Well, thank you for your nice introduction, David, and welcome to everybody to our first Saturday morning physics talks. As David pointed out, everything is made of atoms, with one exception. Anybody think of that? Many. An atom itself. And so the question, what are atoms made of? And I want eventually just to take you on a tour, sort of peering with my bit of experimental apparatus here, closer and closer at different forms of matter. Gas, this fell off. Gas, liquid, and solid. I mean, you're all familiar with gases. There was a very nice show of gases here. I get to play with it too. And what goes on inside a gas is there are a lot of atoms floating around there, but they're all hardly seeing each other, bouncing around, filling up the entire space. Like the air in the room, it fills the entire space. A next simple form of matter, which are actually much more complicated, are liquids. For example, here is liquid, and I've just learned that if I shake some of this hot pepper into it, it turns a nice color. Does it work? It works. How is this different from a gas? What happens in here, of course, is that the atoms inside the liquid like to be attached to each other. They like to be bound together. And so this liquid just sits on the bottom here. If I have a bag of liquid and I open it up, the liquid doesn't come flying out as if I were to break the balloon. The gas would come flying out. Third simple form of matter are solids. For example, the metal in this table here. And if you look deeply inside a solid, where's my magnifying glass? Like so. What you see are atoms in a very nice array, a crystalline array like this. Where each of these would represent an atom. There, of course, are not these little sticks joining them together. Atoms are held together by electrical forces. But you'll see nice, very, very pretty structures like this. And these are the things that physicists love to play with. I was talking about this in one of the elementary schools 2 years ago, and I suddenly realized, I said, everybody, look around you. Everything is made of this kind of stuff. And I couldn't find any examples. Can anybody think of a matter that isn't of these very simple forms? How many people cannot think of matter that's made of these simple forms? Cannot think of it. Raise your hand, if you can. Okay, now take a good look at your hand. That's an example. I mean, this stuff, skin, cloth, hair, none of this stuff is, it's obviously not a gas. It doesn't fly away. It's not a liquid. If I turn it over, it doesn't fall out on the floor. And it's not a solid. If you look in carefully, it's not rigid the way a solid is. Skin bends very beautifully. And there's a whole class of materials that physicists are first beginning to look at. Things like plastic, organic materials, very, very complex systems about whose properties we really know very little about. Here's a nice example of how one gets from liquids to solids to gases. What you're supposed to see here. Since it's put this way, you have to imagine gravity is going that way. Okay. Now, what I'm going to do is turn. Is there a cover here? Yeah. Cover is very important, otherwise the balls go flying. I don't want these big balls. Now, notice when the balls fall in the bottom here, notice it's a little difficult to see, but they actually they're trying to form a rather nice little crystal array. There's some ordering here. They form these nice little stacks where if you look carefully, the structure here are little triangles. You see 3 balls forming equilateral triangles here. This is what a system is like, a solid is like, and any material is very, very low temperatures. There are a few exceptions, but when things are very, very cold, they're in the form of solids. As you begin to heat it, now, when you heat a solid, when you heat any material, you give the atoms some energy and they start jiggling around. And so this is sort of fake heating. What it does is vibrates. And so notice that as you begin to vibrate it, what happens is that the little atoms here are no longer in this very nice, beautiful array, but they all sit at the bottom here. This is very much like a liquid. Now let's heat it a little more. Now what happens? Now they begin to fly all around, very much like a gas. And so as you... The nicest part of this, when you turn it on really full speed, the balls go flying all over. The kids like that one. And so what you see here is you start with a solid, heat it, becomes a liquid, heat it further, it becomes a gas. So I'm telling this to these little fourth graders, third graders in school. One kid raised his hand and said, "Sir, that's not true." I said, any solid you heat it melts. He said, "No, no." I said, "What do you mean no?" He said, "Wood doesn't melt." And in fact, many of these fancier materials, like organic materials, don't obey these simple laws of going from solid to liquid to gas. In fact, what happens when you heat wood? It burns, yeah. It burns, so it turns into gas. Now, of course, what happens there is the oxygen in the air begins to interact with the wood molecules, whatever carbon and such. What would happen? Think about what happens if you burn wood in a vacuum. Well, you can't burn wood, but imagine you heat wood in a vacuum where there's no oxygen. Then what happens? I don't know the answer. I'll leave it to worry about here. Here's actually a picture of atoms. Atoms are very, very tiny things. But actually, let me start with this one here. This is sort of what atoms look like. Atoms... sorry. Thanks. Atoms are something like 100 million atoms would fit in 1 inch if you just lay them out right next to each other. Really very small, very hard to see. And it's really only recently that people have been able to see atoms. And in fact, here is a very beautiful photograph of individual atoms. Each of these little blobs here in indium antinomide. This was taken actually in the physics department here with a scanning tunneling microscope. And you really see the very nice crystalline array that in here. But what is amazing about this photograph is the detail that you can see at these very, very tiny levels. As I said, atoms are about 100 million of them to an inch. If you just were to lay them side by side. Very, very small. What an atom consists of, and now we're done with everything being made of atoms. Now we're going to go inside, again with the microscope, wherever that was, and ask the question, what do atoms actually look like inside? And I just looked over here and realized that another nice demonstration that I forgot about, which is a beaker of liquid nitrogen. And here's just a piece of rubber. Okay. Now, how cold is liquid nitrogen? How cold? Very. What's the number? I don't know. Minus 300 degrees Fahrenheit. Okay, so this is good enough. Now, what happens is the thing obviously becomes solid, and I'm not strong enough. But here's the... Try again. Okay. It cracks. It becomes a solid. Then when it heats back up, you'll see in a moment it will just become its normal rubber state again. Okay. But what happens, of course, is one is just taking energy out of the molecules by dipping it into the liquid nitrogen. Okay, so back to the center of atoms. What's the pointer? Atoms consist of a little atomic nucleus here, which is very, very small. We'll see how big that is, with lots of electrons going around it here. Does anybody recognize this picture here? This is sort of the classic picture of what an atom looks like. Yes? Say it again? It is absolutely right. This actually is a picture of the solar system. You know, I have this little astronomy program on my computer, and I had to print out a picture of the solar system. But it is a perfectly nice imitation atom as well. You know, in the solar system, the sun sits in the center, and the planets go around. And which is this funny planet that's tilted? Which? Pluto, that's right. Okay. But the electrons, so you can think of the electrons doing something very similar to this. Okay, now let's go deep inside the atom now and ask what does this nucleus in the middle look like? And the nucleus is made of several particles. One's called the proton, and one is called the neutron. And the proton has a positive electric charge, and the neutron has no electric charge at all. The size of an atom, the size of a proton or neutron or in fact the size of a nucleus, is a tiny fraction of the total volume of an atom. I mean, if you were to take an atomic nucleus that's bound these protons and neutrons, and stack them across, about 100,000 would be the width of the atom. So the nucleus in the center is about 1/100,000th of the size of the atom itself. And the atom itself is about, 100 million to an inch. So this is, if you line these up, you would get something like 1,000 billion. 1,000 billion nuclei would take up an inch. They're very, very small. Here. As I said, the protons have electric charge, the neutrons have no charge. The chemistry of atoms or different systems is really determined by how many protons there are. Chemistry has entirely to do with the electrons. It's where the electrons of different atoms, when they're brought together, interact together. And since the protons have an electrical charge, the number of electrons going around it is since electrons have negative charge, protons have positive charge. In order that the system be electrically neutral, the number of electrons must be exactly the same as the number of protons. And so it's eventually the number of electrons that determine the chemistry. But the number of protons has to be the same. So the different chemical elements are characterized by saying how many protons they have, or equivalently, what is the electrical charge on the nucleus. For example, oxygen consists of 8 protons and about 8 neutrons. This is called, if it's 8 protons and 8 neutrons, one calls it oxygen 16, being 8 plus 8. Then there's oxygen 15, which has 7 neutrons, oxygen 17, which has 9 neutrons, but always 8 protons. And so the chemistry of oxygen is always the same, independent of the number of neutrons, because it's the electrical charge on the protons. Lead, for example, a lead atom has 82 protons and around 126 neutrons, give or take 5 or so. And you find different forms of lead with various numbers of neutrons inside. Then the very simplest atom is the hydrogen atom. The hydrogen atom consists of a single proton with its electrical charge and a single electron going around it, very much like the moon goes around, like the moon going around the Earth. Interesting question here, however. If the protons have positive charge, and we know positive charges repel. I should have a demonstration, imaginary demonstration. There's a rack sitting here and 2 balls hanging down, and we charge both of them positively, and then they snap apart. Charge one negatively, one positively, they attract each other. So and of course, it is the positive charge of the nucleus. The atomic nucleus has a positive charge, and that's what holds the electrons in place. The electrons have a negative charge, and they just attract together. But there's a serious problem, which is what holds the whole nucleus together? I mean, these protons have a positive charge, and they're pushing each other apart. The answer is there must be some other force that is responsible, beyond the electrical force, that's responsible for holding the nucleus together here. And in fact, what happens is the protons actually are attracted to other protons by this other force called the nuclear force. Protons are attracted to neutrons, and everybody just likes to be very close to each other and form atomic nuclei. In fact, the neutrons play a very important role. There's only one atom, one and only one atomic nucleus that does not have neutrons. And that is the hydrogen atom itself, which is a single proton. But once you get to anything more complicated, anything heavier, you find that there must always be neutrons present. For example, you can't have a system just of 2 protons. A system that has 2 protons alone, the atom is helium. And helium comes in basically 2 kinds. There's helium with 2 neutrons and 2 protons, which is helium-4. and that's the common form of helium. There's also a much rarer form called helium-3, which is 2 protons and 1 neutron. Then there's a very highly radioactive one, helium-6, which has 2 protons and 4 neutrons. However, you never find a helium just consists of 2 protons alone. So the neutrons must play some role in holding the whole atomic nucleus together. Okay, well, let's take one of these protons or neutrons and peer deep inside it and ask what it is made of. And so how do you do this? How do you actually try to look inside a nucleus to understand what its components are? If you look inside, one way of seeing nuclei is you take an accelerator. And we used to have one running here out by the power plant that shoots out a beam of electrons. And the electrons are very much like if you want to figure out what's in a room, you into a dark room. How do you figure out what's inside? You take a flashlight. You shine the flashlight around, and things bounce back, and then you get this light coming back at you, and your brain's very clever, and it figures out from the light that comes back what the object is. This is not very, we're trained to do this. I mean, you shine it and say, that looks like a toaster. You don't say, the light sort of resembles that of a toaster. I wonder how to analyze it. You say, immediately you recognize it as a toaster. Well, physicists get good at this, doing the same thing. Only instead of using light, which has very long wavelengths on an atomic scale, what one uses are very, very fast electrons. So you send a beam of very fast electrons through the nucleus, and you look at they come scattering out in different directions. And you look at these various electrons as they come out, and then go backwards and try to figure out what the nucleus itself was made of. That's one of the very important ways of learning about what the nature of how the atoms, how the neutrons and protons behave inside an atomic nucleus. Very, very accurate experiments, and the University of Illinois is one of the principal centers where such work is carried out. In fact, this entire technique of studying the inside of an atomic nucleus by using electron beams was invented here it's probably about 40 years ago now. Okay, well, one can go one step further and look into the proton or neutron itself. And this requires a finer microscope than one has simply for looking inside the nucleus, because you want to look at even finer details, but they're much smaller. And so if you look inside the proton, you have to use faster electrons, but you can do exactly the same kind of experiment. And various places that do such experiments are, for example, at the Stanford Linear Accelerator in California, in Stanford, near San Francisco. There's a new machine being built in Virginia called CBAF. It's a horrible name. Continuous Electron Beam Accelerator Facility, which enables one to look deep inside not only nuclei, but inside the neutrons and protons themselves. Well, what you see when you look deep inside the neutron and the proton is that it's not just what happened to tennis balls here? Here's a proton. This is a good standard proton. Here's an electron. You shoot the electron here, and if you're just doing this bouncing off a tennis ball, it bounces off, and it appears to be a pretty solid thing. What you discover, however, when you do the same experiment with electrons shooting through a proton, is you find that there are little parts inside, little things are rattling around. And what you discover is the proton itself is not an elementary particle. In the same way as we see that an atom is not an elementary particle, but has parts inside. An atom is made of a nucleus with electrons. The nucleus itself is made of protons and neutrons. The protons and neutrons themselves are made of more fundamental objects, which are called quarks. Made of little funny things called quarks, invented by two physicists, Gell-Mann and Zweig, in the early 1960s. And in fact, in studying various elementary particles like protons and nucleons, people began to see various regularities. And there was this funny way of explaining it by saying, suppose these things were made of suppose the proton and neutron were made of three of these funny things called quarks. They could fit together a lot of data. Things made sense. In the same way, you can begin to understand the periodic table of the elements and all the chemistry of the elements. We can't understand chemistry, but I mean, you can understand why there are different elements in terms of how many protons and neutrons there are. Just the electrical charges on the atoms give you insight into chemistry. Well, in the same way, but these people said, well, if we pretend they're made of different particles inside, we can understand a lot of the regularities that one sees. And certainly for 10 years or so, people didn't believe these things were real. And then there was a very crucial experiment, which is the one I described, where you take an electron and shoot it in to the proton, and you see these things rattling, you see different parts rattling around. And so the quarks really are real objects. They're in there. They're very strange. They come in, the simple quarks come in two varieties. There are actually six different quarks total, six different brands of quark. The two simple varieties are they have silly names. One is called the up quark and one is called the down quark. There's nothing, not that anything sticks up or down, or the up quarks go to the top and down quarks go to the bottom. They're simply names. Then there's this, beyond this, there's the strange quark and the charm quark and the top quark and the bottom quark. Those are just fanciful names for these. Now what's funny about these things is that the up quark has a charge that's 2/3 that of the proton. The down quark has a charge that's minus 1/3 that of the proton. In other words, the three down quarks has exactly the same charge as the electron here. And so how do you do this? For example, to see how you can build up the proton and neutron from these funny particles. A proton is made of two up quarks and one down quark. And so what is the total charge in units of the electrical charge? The proton is a positively charged thing. You have to come out with 1 unit of charge. And so 2/3 for one up quark, 2/3 for the other, minus 1/3. That's 4/3 minus 1/3 is 1. Now what about the neutron? How does that turn out to be electrically neutral? Similar arithmetic. You make it out of 2 down quarks and 1 up quark. Well, if you do that, then the charge is 2/3 from the up quark minus 1/3 for each of the down quarks, and that's 0. And so you begin with these funny little building blocks. Was this? I know in here. This is sort of physicist Lego. These quarks you put them together to make all the pieces. From these little building blocks, one can begin to understand how the neutron and proton get their properties. And so the question is really, what holds these things together? What is the nature of matter like if you peer deep inside here and start to worry about, for example, what holds the proton and neutron together? Why do the quarks want to stay together? I mean, it's certainly not the electrical charge. I mean, here, there's these two up quarks here have a rather big electric charge, 2/3 and 2/3, and the down quark has a charge minus 1/3. Well, these guys are pushing each other apart, and it seems that they would just come flying apart again. There's some other force, which is the eventual thing that gives rise to the nuclear force that holds neutrons and protons together inside a nucleus. That force holds the proton and neutron together. And it's a very strange force here. This is the force that's called gluons. In some funny sense, these are held together by, well, it's almost like electromagnetic energy, but it's something different. It's called gluons. There are particles of these associated with this force, which have the name gluons. And so when young Mr. Herzog, the little one, says, what is everything made of? The answer is gluons. That's half the answer. The answer is gluons and quarks. Quarks being held together by the gluons. And in a sense, what happens is you can think of these things as here's these two quarks playing catch with themselves. This is a gluon. They keep throwing this back and forth. And for reasons that are too complicated to explain, this tends to make them want to be together. It's a little bit like the effect of, imagine two people are lying on a mattress, a very mushy mattress. One person lies down, the other lies down, and what happens, the mattress sort of sinks and they get pulled together. So it's a little bit like, very similar to that. So the gluons are holding everything together here. And so the question is, can you really begin to see isolated quarks? You know, obviously you can take a proton or take a single electron. Here's an electron, here's a proton. And you can make these things and study them individually. Can you study an individual quark? Is this just some mathematical picture? How do you see if these things really are real? Well, what you'd like to do is take one of these and take it out and look for it. Nobody's ever been able to do this. And it turns out you cannot make an isolated quark. They always come in groups, either three attached together to form a proton and three to form a proton or a neutron. Or in addition, there are things called mesons. I haven't told you about antiquarks. There's antimatter versions of these as well. And a quark and an antiquark also glue together and form what is called a meson. And I guess anybody going to talk about these later? Maybe. Good. Okay. I'm not. No. So, but as I said, nobody's ever been able to find an isolated quark. And it turns out there are very fundamental reasons for this. For example, what happens? We're going to do an experiment. We're going to try to make an isolated quark in our heads. So here's a nucleon. A neutron. Nucleon is a code word that physicists use to mean neutron or proton. It's like person is, instead of male or female. See, let's try to take this little green quark out. How do you do it? You start to pull. Okay? You pull and pull and pull, and it's sort of held behind by these gluons. Think of the gluons almost like rubber bands. What happens if you pull a rubber band far enough apart? It breaks. But it doesn't break. It breaks over here, but the way it breaks is it forms a new quark and a new antiquark here. And this new quark over here goes back with the ones that are over here, leaving a particle like a nucleon or maybe something a little different. But the three quarks. And this antiquark gets together with a quark over here, and they form a meson. So what happens is you try to pull a quark out, and you end up with a quark and an antiquark bound together. And it's exactly the same problem as if you try to take a string, okay? Now what I want to do is, the string has two ends. But what I'd like to do is cut an end off and have a string. I want to study a single end of a string. How do you do it? Very easy. Here's the string. I'm going to cut this end off, okay? I can't do anything this morning. Okay. I've just cut the end off. But what has happened? There's another end. I haven't succeeded. I can't make a string with one end by cutting a string in half. Another nice example, which was here. Very nice example. These are magnets. Here's a magnet. And you see, if you know, wonderful. This is a south pole, this is the north pole, and they attract. They don't do anything with this stuff. Unfortunately, somebody put duct tape on the back, and the duct tape just holds it in place. But anyhow, you can see these do attract each other. If I turn this around, it repels and switches around. Okay, now here's a magnet. This obviously has a north pole and a south pole. And so what I want to do is I want to cut the magnet in half. I would like to study an isolated pole of a magnet. There's a single north pole without the south pole. It's like trying to get a single quark without any others attached to it. How do you do it? Well, obviously you break it in half. This is a trick. There's actually two magnets. Okay. Now I said, I've just lopped off the north pole over here. But have I? Probably. Let's see. Here's the south pole. Yep. Huh? These are mislabeled. What? Okay, this is obviously two north poles repelling each other. I turn this around, the south pole. It's never works. Okay, but at the other end, however, let's try this. There, okay, this. Okay, here's the north pole, and I don't get this. No. Anyhow, the point, however, if this would work, it would work. The point is that when you cut a magnet in half, you end up with a north pole on one side and a south pole at the other. You can't isolate a single pole. There's always the other end that goes with it. And it's exactly the same. Take these defective magnets back. It's exactly the same with quarks. Every time you try to take the string out and pull an isolated quark, the string breaks, you make a quark and antiquark, and so you end up with the antiquark attached to the quark, and the one quark goes back with the other to form the unit of three. Where does the energy come to make this quark and antiquark? It comes to the fact when you pull the string, you have to put a lot of energy in. So that energy gets converted into making quarks and antiquarks. What I want to turn to now is the question of, we've seen how there are solids, liquids, and gases. Can one begin to study liquids made of the quarks alone? Not just quarks that come in little bundles making nucleons and stuff, but can you really get quark soup as well? Which is a very interesting project that's going on now, trying to make some form of quark soup. And the idea is the following. Suppose you take atoms in a gas, and you squeeze the atoms together. For example, suppose you take I'm looking for some metal. There's no metal here. You take scissor atoms, okay? Whatever scissors made of steel, iron atoms. And you take them far apart and you squeeze them together to form a solid. You eventually get them really close together. What happens inside the solid? What happens inside the solid is that the electrons get so close to each other. The electrons from different atoms get so close to each other that an electron doesn't know whether it belongs to this nucleus here or this nucleus here. And so some of the atoms start moving around freely. And that's why metals conduct electricity. These electrons carry electrical charge, and they just become free to move throughout the system. So you plug a toaster in the wall, and the electrons start from one end of the plug, go all the way up one of the wires through the toaster, come back out the other here. And so that they're free to move around inside a metal. And so what happens when you begin to squeeze atoms together, you get a system, or this time a metal, in which the different parts that make up the atom become free to move around. So you have, in a metal, the electrons are free to move around, there's still the atomic nuclei there. Then you can ask the question, suppose you take atomic nuclei themselves and squeeze them together. This is a little hard. We're not strong enough to just take, if you squeeze your fingers together, the nuclei don't get very close. In fact, even you're sitting in the seat here, and somehow you're not squeezing your pant molecules very much into the chair molecules, the nuclei. What happens is there are electrons in between. The electrons, because two electrons don't like to be in the same place, you're prevented from falling through your seat here. So it really is very hard to squeeze these together. But nature has a very nice way of doing this, which is, for example, in supernova explosions in old stars. Atomic nuclei, I'll come to that in a second. What happens is atomic nuclei get squeezed together, and what happens is they form a liquid called nuclear matter, which is not like the actors, the players here are neutrons and protons swimming around, but it's like a big, instead of having just a few together, you get big soups of neutrons and protons. This is heated up. You will see it's become flexible again. Even these little broken pieces became flexible. Okay, now, as I said, one can actually make these things inside one can. They are made inside collapsing stars. For example, there is this wonderful event. This happened in 1987. There's a star in a neighboring galaxy called the Large Magellanic Cloud. This was probably out of order. It doesn't matter. And this star suddenly decided one day to explode. We saw it on February 23rd, 1987. It actually happened around 150,000 years ago, but because the Large Magellanic Cloud to neighboring galaxies so far away, it took the light 150,000 years to get to us. And so what you see here is here's a picture that was actually taken, it says, at the University of Illinois in 1983 of the Large Magellanic Cloud. And you don't see very much over here. There's a star in there. However, shortly after, on February 24th or so, this thing got very, very bright, this star. This is successive days. Astronomers have a very, very funny way of labeling things. This is February 22nd, 0.47. You don't tell time, and you tell time's 11:15. You don't say 0.47. What this means is 47 100ths of a day. Here, this is 23 plus 44 100ths of a day, and 24:45. What you see here is suddenly here's the star over here now. There's nothing here. Then it begins to get brighter, and it gets brighter and bigger still. What was happening in there was a old star. There's this star over here called, I can't even pronounce it, Sanduliak. Suddenly ran out of fuel. The nuclear burning processes stopped because nothing left to burn, and the thing began to implode, just fall in. There's no longer enough energy to hold the star up against gravity, and gravity just began to collapse it. And one of the things that happened in doing so is that the various atomic nuclei in the center got squeezed together to form this nuclear matter. And in fact, very likely, this one beautiful step further, which is all the matter in the center got squeezed together to form what is called a neutron star, which you'll hear more about. David Pines will talk about it in a few weeks. This is a star that's about 6 miles, about 10 miles in diameter or so, 15 miles in diameter, weighing about the same as the sun. So if you can imagine taking the entire sun and squeezing it down and fitting it in the radius of Champaign-Urbana, that's what a neutron star is. It's the heaviest, the matter is extremely dense inside neutron star. But the matter there is, inside the star is in the form of a neutron and proton liquid, a form of liquid nuclear matter rather than individual nuclei. Okay. Now we can go one step further and ask the question, is it possible to actually take nucleons themselves, which are made of neutrons and protons, and squeeze it together? The analogy is what would happen if you take grape and squeeze them together? You get grape juice, obviously. And so can you turn nucleon grapes into nuclear grape juice? What would happen? Very much like in atoms, when you squeeze these things together, then the quarks become able to move all around, and you end up with a soup which is made of quarks, and if it's hot, there'll be some antiquarks around and also some gluons running around. And this is some stuff that's called either quark matter or quark gluon plasma. And one project I've been very involved in for the last 10 years is trying to see whether one really can make this stuff in the laboratory. And what I want to do in the last few minutes, when do we get hungry? When does everybody get hungry? 10 minutes, okay. Just discuss how one can go about trying to do this in the laboratory. Well, this kind of quark matter is actually, I like to think of it as a new form of matter, one we're trying to make, but that's actually not true. It's the oldest form of matter. In the very early universe, up to about a microsecond after the Big Bang, as I'll describe, the matter was in the form of this quark matter. It's the densest matter one can ever hope to make. It might be made in the cores of a supernova explosion as stars collapse. Things make it dense enough not only to squeeze the atoms together to make to get metals and such, but to squeeze the nuclei together to get nuclear matter, but nuclear matter liquid. But also, it may be dense enough to squeeze the nucleons together to make this quark matter. And it may be that neutron stars inside their cores, deep inside, like deep in the mantle of deep under the mantle of the Earth in the core, that may also be made of this quark matter. One just doesn't know. But there will be possibilities of finding out with future X-ray telescopes from which one we'll get a lot of information about what neutron stars are made of. Let's go back to this question of the early universe. Now, if you look at the early universe, if you look at the universe, you see lots of galaxies. And one interesting feature of the galaxies, they're all moving away from each other. The universe is expanding. This raises the interesting question of, suppose you take a movie of this and you play the movie backwards, what do you see? Well, if you play the movie backwards, you go further and further back in time. And the galaxies are beginning to move in towards each other. And eventually, very much like these neutrons or protons getting squeezed together, you eventually see the galaxies squeezed together. Then early on, this is really way back, billions of years ago. These things are in the form of a liquid. And further back, this liquid was even denser. And in the very beginning, which physicists like to call a time called the Big Bang, when we think of the universe as starting, but of course it didn't start then. When everything was squeezed together, we have no idea how to describe things before that, what life was like then. But we could trace this back to some time about 10 billion years ago, when the first time when we can describe what's happening in the expansion. And so, if you look back in time, then after about a millionth of a second, the universe is up to a millionth of a second. The universe is filled, all the matter of the universe, the stuff that eventually becomes us, and stars and tables and such, was in the form of this quark-gluon plasma, in which the principal actors were just the quarks and gluons running, and antiquarks running around. After about a 100,000th of a second, the first thing that happened were nucleons began to form. The quarks, one got little bubbles in which the quark, as they got further and further apart. Remember, I told you quarks don't like to get far apart from each other. These little strings want to hold them together. And so as the universe expands and these want to get further and further apart, they start to form these little lumps called nucleons, neutrons and protons and such, and various mesons. And so the universe expands, and then very rapidly it fills up with just the neutrons and protons. And about in the first 3 minutes or so after the beginning, the neutrons and protons get together to form light elements like, well, one has hydrogen, and then the hydrogen and neutrons, protons and neutrons get together to form helium atoms. And in this way, various elements are made in the very beginning. Most of the elements that we know were formed much later, were formed in stars. I mean, originally one just has neutrons and protons, and some helium, maybe a little lithium, a little deuterium. But things like carbon and such were not made this way. The carbon is made from burning helium inside stars, inside the sun. The sun is burning hydrogen to form helium. Other stars burn helium to form carbon. Carbon forms carbon and helium get together to make oxygen. And various chemical elements are made in the stars, which is very interesting. Because we're made, with lots of carbon inside of us. And so what does that mean? It means the stuff inside of us, we were once inside stars. The stuff we're made of, the carbon and such, was formed by burning this primitive stuff. The hydrogen, the helium, and the hydrogen was formed in the Big Bang by burning that inside stars. And so what the stars so the question is, how did we get from being inside a star to being here? Any ideas? The answer is supernova. What must have happened is carbon forms inside stars, oxygen, all our nice parts, and iron. The stars must have exploded. So the star that held our atoms must have exploded, and then eventually cooled down and formed things like the Earth, where we were made. I discovered, I should have told you, here's a nice picture of what goes on inside a supernova explosion, which I didn't have a chance to discuss. What happens there is that the star loses its pressure as it can no longer burn fuel anymore. Gravity then begins to pull it in. A very dense core is made. This is where the nuclei are squeezed together. And then some magic actually happens, which is that the matter goes in and it bounces back out. As it bounces back out, it comes flying out here. And what you see in these pretty pictures of supernova explosions is this outer shell here of matter expanding out. But one is left with this neutron star, usually deep in the center, which is a very, very dense object that David Pines will talk about. I've actually drawn a mountain to scale here. The mountain's no more than some tiny fraction of an inch high. That's the highest mountain you can have. Gravity is very, very strong. Gravity, you try to make a higher mountain, gravity will simply pull it down. What's the highest mountain you can make on Earth? What is the highest mountain there is on Earth? Everest. How tall is Everest? About 5 or 6 miles high. So around, that's maybe a few miles more, but if you had much more, try to make a mountain much higher on Earth, gravity of the Earth would simply flatten it, pull it down. Same thing here, but the highest you could build it on a neutron star is about a 16th of an inch. This is not a trivial mountain, however, because the energy involved in climbing, gravity is so strong that the energy that's involved in trying to climb such a mountain would be far greater than you could ever do in your lifetime, put out your mountain in your lifetime. Gravity inside these things is exceedingly strong. Okay, so let me turn to this question now of how one might hope to make quark matter inside the laboratory. In fact, generally, how do you study very, very dense states of matter inside the laboratory? Here's sort of a rough picture of what we think things look like. Here. This is sort of what I'm showing here is how dense things are compared with how hot they are. Now, this is a very funny picture. This is on the scale of inside the atomic nuclei, where this is 10 to the 14th grams, or 10 to the 11th pounds per cubic centimeter. Matter is extremely dense here, and extremely hot. This is some 10 to the 12th degrees here. We are way down in this corner here. I mean, all of common physics exists down in this corner. However, the early universe is way up here, very, very hot, and relatively not too dense. As time goes on, the universe cools down and comes down like this. Neutron stars, supernovae sort of go about like this. As the star implodes, it gets denser and denser. As a supernova explosion, it settles down someplace here. When matter's very squeezed together, or very heated even, it turns into this liquid called a quark-gluon plasma here. Whereas ordinary nuclei, the matter is way down here, relatively cold and very dense. But there's this region way out here that we'd like to study, where matter can be in the form of this quark, just quarks and gluons. Now, the way to do that is to take big atomic nuclei, like two gold nuclei, and just bang them into each other. Now, the energy with which this is being done, particles have, any mass has an amount of energy called its rest mass. And rest energy is the mass times the speed of light squared. And these have an energy, just kinetic energy of motion, which is about 100 times their rest mass. This is called a GeV. Now, what happens is you get these big nuclei colliding into each other. This has almost been done. Big nuclei colliding into each other, and they're so energetic, what happens is they pass through each other. You know, it's almost like a bullet going through a thick door. It passes through, and then it begins to break up. So these nuclei pass through each other, come out the other side. So here's 1 and 2. Notice 1 has gone to here, 2 to here. But what's happened, they've left a lot of hot debris in between. And so they're moving apart from each other. They come in like this, pass through each other. It doesn't work too well. Pass out like this, leaving this very hot debris in between. And this stuff here looks very, very much like, we hope, this quark-gluon plasma. Just a lot of, one hopes to leave together a lot of quarks and gluons and antiquarks in this region here and hope to study it. Now, there's some difficulties in doing this. One is it's very small. The entire size of this is perhaps 1 part in 10 to the 12th of a centimeter or of an inch. So 10 to that is 1,000 billion of these lined up would be an inch. Doesn't last very long. I mean, typical rate at which processes happen inside nuclei is some 10 to the minus 22, 23 seconds. If you have difficult, are you familiar with this kind of notation? 10 to the minus numbers? What it means is it's a billionth of a billionth, a 10,000th of a billionth of a billionth of a second. It's very, all you have to remember, it's very short. It's very, very, very short time. And it's very hard to see how can you ever hope to learn about something so tiny that lasts for such a short time. The matter in here is one hopes, we hope, will look something like the matter inside the early universe. You know, one hopes to be able just to recreate conditions that one had inside the early universe. How do you learn about it? Well, what's going to happen is things are going to come flying out of here. It's not going to last forever, and this matter is just going to be converted into more usual-looking things like neutrons, protons, and other particles. And what you have to do is measure all these particles out here, and it's going to be a very big game to go back from these and translate back to figure out what life was back here, but we're hoping to do it. Where is this actually going to happen? There are some experiments underway now, which I'll tell you very, very briefly about. At Brookhaven National Laboratory, which is on Long Island, and also CERN, which is now called the Center for European Nuclear Research, which is in Geneva, Switzerland. Starting around 1986, people started trying to figure out how to do these experiments. First, they took light nuclei like oxygen or silicon or sulfur and bashed them together at somewhat lower energies. And so a lot of these prototype experiments have been done so far. Just 2 years ago, Brookhaven began to use gold nuclei as well. And there is being built right now something called a big machine called the Relativistic Heavy Ion Collider, which is called RIC, which is going to take big nuclei like gold and smash them together. I purposely use this old view graph over here to give you a feeling for how things don't happen in science now. I first got involved with this machine in 1983. I said, and I gave a talk where I laid out the time it would take to build it. 1989, we begin to experiments. And somebody in the audience, a learned man, said, does it have to take that long? Then various budgetary problems got delayed finally to 97. And this was good last year. Now it's changed to 99. Huh? It may, but maybe. Then similarly, it's not only the Americans who are having these problems in funding science, the Europeans as well. CERN had planned to build also a facility for putting in, for colliding very heavy nuclei together, not just the light things. Their favorite nucleus is lead rather than gold, for no particular reason. And that was planned to be in 1992. And then that got delayed now. But actually, this one is really happening right now. The experiments are just beginning this fall. Then CERN has also planned to build something called, put in heavy ions in a machine called LEP that's there already. Now it's planned to be 98, and then it's 2000. And if you read the newspapers now, there are discussions about whether it will get built at all. That's another difficult one. This is sort of what these things look like. This is, if you look at Brookhaven from the air, do you remember a few years ago there was something called crop circles that were very fashionable? These were these mysterious big circles that were seen in England. Well, if you fly into Kennedy Airport in New York and you fly over Long Island, you see this enormous crop circle. It's probably the world's largest crop circle, which is where this, the crop circles turned out to just be fake. Man-made, this is also quite man-made, where there's this big tunnel here, and this is about, from here to here is about 2,000 feet. And this is about 2.5 miles around here. And what's going to be done there is gold is going to be produced here, whizzed around through various accelerators, the smaller accelerator called the alternating gradient synchrotron, eventually get put into here, and you notice how this divides in two. We'll get one beam going this way, one beam going the other way. These beams will counter-rotate, and it's arranged so that every now and then they'll cross each other. And when the beams cross each other, they will collide together, and then there'll be various experimental stations set up to measure these things. These are some old pictures of what it looked like inside the tunnel here. This thing is actually getting filled up right now with gigantic magnets. um, which look basically like this, large things. These things, this is about 40 feet long here. Are there pictures in there? And so eventually, this tunnel will get filled with these magnets, and I hope so. I mean, I heard they're being built by Grumman, the aircraft company in Long Island. I just heard in the news this morning, Grumman is firing 6,000 people now. So I'm not exactly sure what effect that will have here. But anyhow, we hope that by the turn of the century, one hopes to be able to begin to do these experiments. And I just want to show you a picture of one of these very preliminary things that have been done. This is the result of taking, this is a oxygen nucleus smashed onto a lead nucleus. This is done at CERN in Switzerland. And what you see here, you get some feeling, here's where the original nucleus was. And what you see coming out of this is a lot of stuff. You know, hundreds and hundreds of particles come flying out. And when these experiments are done in Brookhaven, probably 10,000 or more particles will come flying out. And there's an enormous problem of trying to decipher each and every one of these particles, figuring out what they are, how fast they're moving, which way they're moving and such. One hopes from that to be able to go back and learn what was inside these nuclei as they smash together, and whether one could indeed begin to make new states of matter like the quark-gluon plasma and such. So the only thing I can say to you at this point is stay tuned for another 10 years or so. And this, I guess, ends my tour of what everything is made of. Thank you.